right, check, check. We should be going live here. Come on. Let's go. Here we go. Going live. All right. Check, okay. All right, guys. So we're going live. I am just going to start recording here. You can post questions in the chat, but really what I'm going to do is I'm just going to go through a lesson and maybe hold your questions, or there might be some parts during the lesson where I stop to answer questions. But I'm going to record my lesson on YouTube. The reason why we're doing it on YouTube is because we were instructed by the county to kind of shy away from Blackboard Collaborate for a little bit as we're trying to figure out if it's going to work or not. So I'm going to film my lesson on YouTube. Okay. So are we going to have first period, third period, fifth period, seventh period today? It's really up to your teacher. You can try. We were told that we could try, synchronized learning, but the county's really pushing asynchronized learning. So what I'm going to do is I'm going to record the lesson right now. So first period, this is our normal class time. Really, we're 15 minutes early, but okay, whatever. So I'm going to record it now. You can watch it. And second and sixth period, or second and eighth period, I encourage you to watch it before Thursday so you can get a head start on this work. You're already, a week behind. So I would encourage you to watch it then. So what I'm going to go over today is reaction mechanisms. So I've over them before. So you might want to go back and look at the video that's posted there. But we've already gone over them. But I'm going to go over that. I'm going to do the practice. I'm going to do the homework quiz 7.1 because after our discussion on mechanisms, we should be able to answer all the questions on that homework quiz. So that'll be today's lesson. And after that, you should go to work. Remember, on Thursday, from now on, Thursday afternoon, I'm going to go over practice tests. So this Thursday, I'm going to be doing practice test number 3 on Thursday at 3 o'clock. So I'll be going over the answer key there. So if you want to do a practice test or just go over with me, meet me there on Thursday. Okay. So, okay. So we're going to go ahead and get started today on reaction mechanisms. No, we're meeting right now. So our normal time is 9:15. We're meeting right now. So no, we're not meeting. We're this will be the lesson. So what you would normally do during that meeting is, well, right now we're meeting on YouTube for first period today, normal time. It might run over. If it runs over and you have to go to your third period class, then go to your third period class. Some teachers might still be doing face-to-face instruction time during first, second, third, whatever period. Other teachers might not be. So I'm just going to film the lesson on YouTube. I'll post the video. Watch it when you want to. Okay. But if you want to watch it right now, you'd have the opportunity to ask questions. Okay. But yeah, so hopefully you've been checking your emails and stuff, and we're being told not to use Blackboard Collaborate. Or we could still try to use Blackboard Collaborate. We're getting a lot of cross messages, so I'm just going to stick to YouTube because it's worked. All right, so here we go. All right, so let's talk about reaction mechanisms. All right, so I posted this last time, so hopefully you all can see it. I just want to make sure that it's going to come up okay in the screen. You have a copy of this. I emailed it to you last night, but you can just kind of follow along. And a lot of you have already, gone over this with me. Hold on, I just want to see if it pops up or not. Okay. All right. So let's kind of review what we learned last week. So last week we talked about the differential rate law. So if I have a reaction, okay, we got 2A plus 2B yields C plus D. If that's my reaction, and I want to write the rate law, the rate equation for that, which we call the differential rate law, it looks like this. All right, that's what it looks like. And really all I have to do is figure out what X and Y are. Okay, so if I figure out what X is and what Y is, and really there's only three possible answers. It could be 0, 1, or 2. Okay, so they could be zero ordered, first ordered, or second ordered. Once I figure out what those numbers are, I plug those in for X and Y, and that's my rate law. That's all I have to say. Okay. A lot of times, as the question progresses, you go from write the rate equation, and then so write the rate equation is basically figure out the reactant orders. Okay, and then after you figure out the reactant orders, now you can plug in some data, and you could solve for K, and then you have to have the right units for K, and you could ask a bunch of different questions. But the first thing to understand is what the rate equation shows us. It shows us how the rate of the reaction, how fast the reaction takes place, and that could be measured in usually molarity per second, molarity per minute. How, what's the how is the molarity of A changing as a function of time, right? So it could be the rate of disappearance of a reactant, or it could be the rate of appearance or the rate of formation of a product, right? If the reaction starts with only reactants, right, then at the start of the reaction, you're going to be losing those reactants and you're going to be gaining products. So we can measure the reaction rate by the rate in which we're losing reactant, or we could measure the reactant rate of how fast we're gaining product, right? So the amount of product produced over a function of time, or the amount of reactant lost over a function of time, okay? Regardless, the rate equation shows us how a reaction, the rate of the reaction, is affected by the concentrations of the reactants, okay? And so we have to figure out what X and Y are, so the reactant orders, right? So, right, if a reactant is zero ordered, then that means changing its concentration won't change the rate. If it's first order, whatever change you do to the concentration, the same thing happens to the rate. If it's second order, whatever you do to the concentration, that number squared is what happens to the rate. So if you double the concentration, 2 squared is 4, the rate gets multiplied by 4. If you triple the concentration, 3 squared is 9, the rate gets multiplied by 9. If you cut the concentration in half, 1/2 squared is 1/4, the rate gets multiplied by 1/4. Okay? So that's what second order means. Okay? And so really there's two ways you can determine, you really can only determine the orders of the reactants through through experimental data. But on a test or a quiz, there's two ways you can determine the reactant, or well, I guess three ways. They can tell you what the orders are. Okay, great. They told you what the orders are. Okay, or you're given data like the problem set number 1 that you worked on last week. Okay, so problem set number 1, it gives you initial rate data, and it has different trials, and it says, okay, well, trial 1 and trial 2, we doubled the concentration of A, we kept the concentration of B constant, and the rate also doubled. If that's the case, now we know that A is first order, right? So you did some practice with that, and that's how we kind of finished up last week, okay? But here's the deal, okay? So you can only be told, so you can only figure out the reactant orders with experimental data. So you have to do multiple trials. You got to hold one of the concentrations constant. You got to do something to the other concentration and see what happens to the rate, okay? And based on how you change the concentration and how the rate changes, you can determine if it's zero, first, or second order, right? Okay. So the other way you could do it, like on a test or quiz, is they could give you what we call a reaction mechanism. And that's what we're going to get into in a second, all right? So let's say we took our lab data and we figured out A was first order and B was second order, then this would be the rate law, okay? If A was zero ordered instead, then this would be the rate law. Notice how A is not included in the rate law anymore because it's zero ordered. Now, you could put A to the 0th power in the equation, but anything to the 0 power is 1, so you don't have to include it in the rate equation, right? Okay, so again, this is just kind of review from last week, and then we'll get into reaction mechanisms. But the last thing I want us to make sure we understand is how to figure out the units for K. And there was, you know, notes that I handed out to you last week, but this is the equation that it will always follow. Now, the unit of time, the reason why I just say time here is because sometimes the unit of time is measured in minutes, sometimes it's seconds, it could be hours, depending. So you just have to, they'll tell you what the rate, rate is measured in terms of time. Is it molarity per second? Is it molarity per minute? Is it absorbance per minute? Is it absorbance per second? So you just got to pay attention. That'll be given to you somewhere within the data. Oh, they were measuring the absorbance versus time versus seconds, or the absorbance over hours. Okay, so time is either going to be usually it's seconds, minutes, or hours. Okay, but notice the units for K are always going to be 1 over molarity raised to the reaction order minus 1. So remember, the reaction order is the sum of the reactant orders. So if this is my rate law for our reaction from the start, right? My one order is 1 and the other reactant order is 2, so 1 plus 2 is 3. That's the reaction order. So all I have to do is the reaction order, which is 3 in this case, minus 1, right, would give me my units of K. 1 over molarity squared times probably seconds. Most of the time it's seconds, but it could be 1 over molarity squared times minutes, or 1 over molarity squared times hours, whatever the unit of time was used, okay? But that's how you figure out the units of K. So what if your reaction order was 1 instead of 3? Well, then it would just be 1 over seconds, because it would be 1 over molarity to the 0th power, which is 1. So it would just be 1 over time, okay? So that can happen, right? Sometimes your K value doesn't need to have molarity. It could just be 1 over seconds or something, okay? Now, just another way to get used to seeing the units, like this would be the units for this particular K value in this rate law when you have a third order reaction, okay? But a lot of times they might be written like this. So remember, molarity is moles per liter, so 1 over molarity is liters per mole. So another way to write these same units right here is this way. Okay, so you might see it that way. So just, don't, hopefully you understand mathematically how that works. Okay. All right. So let's keep going. Yeah, Amy, the reaction order is the sum of the reactant orders. Yep. Okay. So let's get back to it. So again, you can use data to figure out the orders, but now I'm going to tell you how you could use the mechanism. But before you know how to use the mechanism, you have to understand what a mechanism is, okay? So let's talk about it, all right? So if you're given the initial rate data, right, you would just have to look at different trials and figure out, okay, I adjusted this concentration and I kept all the other concentrations the same, and the rate did this, so I know I'm 0 first or second order. Now let's talk about, well, what if they don't give me that data? What if they give me a mechanism? So let's talk about what a mechanism is. All right, a reaction mechanism is just the step-by-step process. It's the step-by-step equations that show the actual collisions that must occur for the reaction to happen. Okay, so the sum of all those steps is the overall reaction. So you could have, like when you get to organic chemistry, you could have a 30-step mechanism. This has to collide with this, and then this happens, and then this collides with that, and then that happens, and then this collides with that, and that happens. We're probably going to be dealing with 2-step mechanisms, 3-step mechanisms, maybe 4-step mechanisms at the most. That's it. All right. And really, we're not even going to be using, a lot of times we're not even going to be using actual chemicals. We're just going to use letters like A and B have to collide, and this happens. Okay. So elementary step is a step that actually shows the collisions that have to happen. So if you're told a reaction, the overall reaction is an elementary step, then that reaction is the mechanism. It's a one-step process, okay? But if we go to this equation, there's no way a reaction like this, could be one step. There's no way that this right here is an elementary step, okay? So what's going on here, okay? If you told me this was an elementary step, what you would be telling me is that 2 A particles and 2 B particles, 2 different A particles and 2 different B particles have to all collide, so at the right orientation. So you're talking about four different particles colliding all at the right same time, all with the right orientation, all with the correct energy, the activation energy to overcome the reaction, right? For the reaction to occur. That's not going to happen, okay? We would call, okay, so the elementary steps are defined by what we call molecularity, all right? And it's really just how many molecules are part of the collision for the reaction to happen, all right? So if you just have A yields B, then the molecularity of that is just one. But if I have like A plus A collides to form, C or whatever, then that's two molecules colliding. The molecularity would be two, okay? So you rarely have molecularity of an elementary step to be above two. You rarely have three or more particles that have to actually collide for a reaction to happen. And if that's the case, if you have more than two particles that have to collide for a reaction to occur, then it's going to be an incredibly slow reaction because the odds that that collision occurs become less and less the more molecules that come into play. Okay? So usually elementary steps are either have a molecularity of one or two, and that's it. Okay? If this were an elementary step, it would have a molecularity of four. Not happening. Okay? It doesn't work. Okay. So that's not how the reaction happens. You could say two A's and two B's collide and form C plus D. No, that's not what happens. There must be another mechanism that allows for this overall process to occur. All right. And that's what a reaction mechanism is. It shows the step-by-step process. Okay. So here's a proposed mechanism. Okay. So before I show you the proposed mechanism for that reaction, understand what the mechanism has to have, the rules for the mechanism. Okay. A complete reaction mechanism. So first of all, it must add up to the overall reaction. So you have to, the sum of the steps have to add up to the overall reaction. Okay. So things have to cancel out so that what I'm left with at the end is the same equation we were talking about from before. So if I want a reaction mechanism for this reaction, all the steps have to add up to that equation. Okay. So that's number one. That's rule one. Okay. Just checking here. Okay. All right. So that's rule one. Okay. Rule two is it has to agree with the rate law. So if you know what the rate equation is, if you know the rate law, then the reaction mechanism has to agree with it. What that means is the reaction mechanism has to show the correct orders of the reactants. Okay. And we'll talk about that in a second. Okay. And then a complete mechanism has to tell you what the rate determining step is. But here's the deal. If I know the rate law, I could propose a mechanism, or if I know the mechanism, I could propose the rate law, right? You could go either way, okay? All right, so let's go to an example mechanism. All right, so what I'm saying is this is the mechanism for this reaction. So what we're saying is this is the overall reaction, but this is how it happens. I'm saying a B particle collides with a B particle to produce C and W. And then a W collides with an A particle to produce a Z particle. And then a Z particle collides with an A particle to produce a D particle. Okay? And what you'll notice is we get these new things. We get these things that we didn't see in the overall equation. All of a sudden we get a W, we get a Z. And notice they're not in part of the overall equation. They're not in there. Okay, well, what are those things? We call those things intermediates. Okay, intermediates are things that get produced and then they get consumed within the reaction mechanism. So they're not a part of the overall equation, okay, and they get canceled out. So notice like when I add up the overall steps of the reaction mechanism, right, I get my overall equation. It's the same equation we've been talking about. Notice that W cancels out. I got a W on this side, I got a W on that side, it cancels out. I got a Z on this side, I got a Z on that side, it cancels out. These are intermediates. Not to be confused with catalysts. We'll talk about what catalysts are in a second. But intermediates, what happens? They get produced in the mechanism in one step, and then in a subsequent step, they get consumed. And it doesn't have to be the next subsequent step. It could like you could have W down here, and if W canceled out, it was in step one and then showed up again in step three and canceled out, that's fine. It's just it gets produced in one step, and then in a following step, it gets consumed. Okay, it's not a part of the overall reaction. Okay, so another thing to notice about a reaction mechanism is if it's a complete mechanism, they have to tell me what are the fast steps and what steps are the slow steps. Okay, the slow steps. Okay, the slowest step is what we call the rate determining step. Okay, the rate determining step. The mechanism, you're only as fast as your like so you're at a relay race, right, or whatever. You're only as fast as the slowest person in the relay race, right? So the reaction, the rate of the reaction is determined by the slowest step, right? That's why we call it the rate determining step, the RDS. Okay, and so what's the RDS in this mechanism? It's this step. That is the rate determining step. Okay, so how do you figure? Okay, so let's say I was given this reaction, right? I was given that reaction, and you were told, or you were said that's the reaction. What is the rate equation? And you would say, okay, well, let me see if they gave me initial rate data. Oh, they didn't give me initial rate data. What did they give me? They gave me a reaction mechanism. Okay, well, I can handle that. All right, so if they give you a complete reaction mechanism, from the mechanism, you can get the rate equation. What would that really mean? What that means is if you have a complete reaction mechanism, you can determine the orders of the reactants, because that's really all you need to write a rate equation, right? You need rate equals K times the concentration of this raised to its order times the concentration of that raised to its order, and so on and so on and so on. Okay, so how do we get the reactant orders? All right, so what you do, all right, how do we get this rate law from this mechanism? What you do is you find the rate determining step. The rate determining step is the slowest step. You go to that slowest step, and you use that step and any previous steps, any steps before the rate determining step. You ignore all subsequent steps. You do not look at those steps. All right? You use the rate determining step and all the steps that led you to the rate determining step. Because the speed of the rate determining step is going to, like, so if you think about it in this case, the speed of this step, yes, it's a slow step, but it's going to increase depending on how much W I get, right? If I don't have any W, this step can't happen. So all the stuff, right? All the steps before this step that result in the formation of W, whatever that is, they are a part of determining how fast the reaction will go. All right. So you use the rate determining step and every step above it to determine the reactant orders. You ignore all the subsequent steps following the rate determining step. All right. And what do? You count. How many times did one reactant show up? All right. So we count. How many times did A show up in this step and any previous step? Showed up one time. How many times did B show up? 2 times. That's the order. So B showed up twice, it's second order. A showed up once, it's first order. Boom, you got it. That's it. That's all you have to do. Okay? Now, just real quick, you could go the other way around, right? What if they said, here's the mechanism, but they didn't tell you the rate determining step? Right? What if they said, here's the rate law, here's the rate law, here's the mechanism, here are the elementary steps, but you don't know which one's the rate determining step. Okay, what would you do? Well, you would say, okay, well, the rate law says A is first order and B is second order. So where do I put the slow step? If I put the slow step here, then that would show B is second order, but A would be zero order because A doesn't show up at all before the rate determining step, right? So that can't be the rate determining step. Well, what if I make the last step the rate determining step? Well, if I make the last step the rate determining step, A shows up twice, B shows up twice. They both should be second order. Oh, okay. Well, that can't be the rate determining step. It must be this one. Okay, does that make sense? Okay, so you could also go the other way around. So if you know the rate law, you could determine what the rate determining step is. Okay, but if you have a complete mechanism, which means you're also told what the rate determining step is, you could figure out the reactant orders, and therefore you could figure out the rate equation. Okay, all right, all right. So again, just so this is the same mechanism, but now this was the slow step. So if that were the case, then this would be my rate law, right? If this is the slow step, it shows B as second order, it shows A as zero order because A doesn't show up in any previous steps and in the rate determining step, but B shows up twice, right? And then if the last step was the rate determining step, then both of the reactants would be second order in this case. Okay. All right. Don't got many viewers here, but do you have are there any questions right now before we move on? Any questions with what I've gone over so far? I'll just take a minute just to answer questions here in the chat. Not many people watching though. So, oh well. Any questions? You can also email me if you have them. All right, we'll get back to it in a second. I just want to, I know there's a delay here, so we'll see. Okay. So let's keep going here. Okay. So the other part is we want to talk about a catalyst. Okay. So we talked about intermediates. Intermediates are things that show up, they get produced, and then they get consumed. Okay. A catalyst does the opposite. Okay. Again, a catalyst is not involved in the overall reaction. A catalyst is not a reactant, it's not a product. Okay. It's but it is something that helps a reaction mechanism, okay? But it provides a different mechanism. So a catalyst, what a catalyst does, it provides a different pathway. So you could have a regular reaction. So this would represent, like if this was the reaction mechanism for our equation that we've been talking about, 2A plus 2B yields C plus D. If this is the reaction mechanism, this would be the uncatalyzed mechanism, right? There is no catalyst involved here. Okay, but that means not all reactions have catalysts, but if the reaction had a catalyst, there would be a mechanism for the catalyzed reaction, and then there's a mechanism for the uncatalyzed reaction. Okay, so here is the uncatalyzed reaction. Okay, here's the uncatalyzed, or sorry, here's the catalyzed reaction mechanism. Okay, and so in this case, we notice that Y is something that it's kind of like an intermediate, but it's not the same, right? Understand that a catalyst is something that gets used and then produced. It gets consumed and then produced. An intermediate gets produced and then consumed. All right. So I always say, like a catalyst cancels out on this diagonal. I don't know if you can see the mouse on my screen here, the arrow on my screen cancels out on this diagonal, right? Let me do that. Insert. I wanted to insert shapes, but okay, whatever. All right. So yeah, here we go. So what I'm saying is a mechanism cancels out on that diagonal, right? From here to here, and an intermediate cancels out on this diagonal within a mechanism. So within a mechanism, if you cancel out on this diagonal, here to here, you're a catalyst. If you cancel out on that diagonal, you're an intermediate. Okay? So in this case, Y is our catalyst. Okay, how do I recognize it as a catalyst within a mechanism? Because it gets used and then consumed. Okay, notice that Y is not part of the overall reaction. Okay, the overall reaction, Y still cancels out, but it's not considered an intermediate. An intermediate is something that gets produced within a mechanism and then it gets used up somewhere else down the line. Okay, a catalyst is something that gets used and then it gets produced. So in the end, it ends up canceling out. It just cancels out on the opposite diagonal that a intermediate cancels out. Okay. Now, a catalyst will be included in the rate equation. So the only things that go into a rate equation, remember, products don't go into it. It's not like an equilibrium expression. Equilibrium expression, products over reactants, coefficients become exponents. Rate equations, it's just the concentrations of the reactants, and the coefficients aren't anything unless you know it's an elementary step, right? You have to figure out the exponents by determining the orders of the reactants, okay? But the other thing that can be included in a rate equation is if you have a catalyzed reaction, the catalyst is included in the rate equation, okay? So let's look at this mechanism, all right? Let's identify the intermediates, right? So you got X cancels out as an intermediate, W cancels out as an intermediate, Z cancels out as an intermediate, right? So all those one right there, the ones kind of in the shaded blue, those are the intermediates. Y is a catalyst, okay? Now, we find the rate determining step. It's this step, so it's the last step. So now all we have to do is count how many times the reactant shows up within those steps and how many times a catalyst shows up within those steps. And those are the orders for everything. So B shows up twice, second order. A shows up twice, second order. Y shows up once. Okay? So this would be my rate equation. A and B would be second order, and Y would be first order. Okay. Now, notice that the overall reaction order for this equation it would be 5, 2 plus 2 plus 1. So if I was looking for like units of K, it would be 1 over molarity to the fourth power times, seconds to the negative 1. Right. Okay. So let's go back here. All right. Now let's just do a little bit of practice here. What if we had said, okay, no, this is fast. Let's say this was slow. How would that change my rate equation? Well, then I would only look at these steps and I would say, okay, Y shows up once, A and B show up once, and then I would go down to my rate equation. So these would all just be, first order. And if they're all first order, now my K units are 1 over molarity squared because my reaction is third order. My overall reaction order is third order. Okay. Well, what if this was actually the slow step? Usually the step with the catalyst isn't the slow step because it's a catalyst, but what if that was the slow step? Then B would end up being zero ordered. So then that would be my rate equation. And then it would be just 1 over molarity times seconds to the negative 1 for my units of K. All right. Okay. So what I'd like to do now, oops, got an email. So the slow step, okay, so you have to be given so the slow if you're going from a reaction mechanism to figure out, if you're using the reaction mechanism to figure out the orders of the reactants, then they have to tell you what the slow step is. But remember, they could go the other way around. They could give you the rate law that has the orders of the reactants, and then you have to figure out the rate determining step. So yeah, usually, so if you have a complete mechanism, that includes the slowest step, the rate determining step. But again, what they could do is, like, let's go back to this one. Okay, what they could do is say, okay, they could say here are the elementary steps of the reaction mechanism, and they don't tell you which ones are fast or slow, and then they tell you this. What if they told you this was your rate law? Okay, so e- either you know the reactant orders, and then you could use that to figure out the slowest step, or you know the slowest step, and then you use the mechanism to figure out your reactant orders, right? You have to know one or the other, right? So what if they told you this was the rate equation? Okay, so they're telling you, if they're saying this is the rate equation for the reaction, they're telling you A is second order, B is first order, Y is first order. Okay, then you go back to your mechanism and say, okay, well, what would have to be the slowest step to indicate that as the rate law? Well, then this step would have to be the slowest step, because if this is the slowest step, A shows up twice, so A second order, B shows up once, so it's first order, and Y shows up once, so it's first order. Okay, so that's kind of a way they could give you the elementary steps of the mechanism, not give you the rate determining step, but what they would have to give you are the actual reactant orders, so then you could figure out what the rate determining step was. All right, so you're either going to be given the complete mechanism, find the rate law, find the reactant orders, or you'll be given the reactant orders, you'll be given the rate law, figure out what the rate determining step is, right? It would be one or the other. Okay. All right. So the other thing I'd like to do is I'd like to go over that homework quiz. So let's do this homework quiz together. Okay. Let's figure this out. Okay. So I emailed this to you last time. So if you have your own copy, you can look at it. But this would be homework quiz 7.1. So after last week's lesson and today's lesson, these are the types of questions you should be able to answer based on kinetics. Okay. There's still one more part to kinetics. That's the integrated rate law. That's what we're going to be doing next week. Okay. But this is the type of question you should be able to answer right now. Okay, based on the stuff we've gone over today and last time. So let's go through it. Okay. All right. So they give us the initial rate data. Okay, and it's the rate of appearance for NOBR. Okay, so it's how fast this is appearing. And notice the units. It's molarity per second, right? Moles per liter per second. So another way to write these same units here, if I was making notes, the other way to write those units here, the molarity per second. It's the same thing. Molarity per second. Okay. So let's go here. Okay, so it says determine the reactant order of NO and BR2, justify your answers. Okay. So what would we do? We would look at the first two trials to identify this guy, right? We would use the first two trials to identify the order of NO. Why? Because we changed NO, but we kept BR2 constant. Okay? So what did we do to NO? We doubled it, 0.02 to 0.04. What happened to the rate? Okay? Now, what you could do is what I do, like sometimes they don't give you numbers that are non-calculator friendly. So what you could do, what I do is I do trial two, I do the big number divided by the small number. So I would do trial two divided by trial one in terms of concentration. So 0.04 divided by 0.02, right? And you get two, obviously. But then what you would do here is do this number divided by that number. If this number, if this number divided by that number is the same as this number divided by that number, then guess what? You're first order. But if it's different, then it's probably second order. If what would have been true if these two numbers were the same, this number and this number? NO would be zero order. So we know at least that NO is not zero order. So what am I going to do? I'm going to do 38 divided by 9.6. Okay, that comes out to be 3.95. So 4. Okay, well, 4 is 2 squared. So what does that mean? It means NO is second order. Okay, justification. I'll increase my font here. Okay, justification. Okay, so looking at trials 1 and 2, we doubled the concentration of NO while keeping the concentration of Br2 constant and the rate quadrupled. Okay, that's our justification there. Okay, so that's really all we have to put. Okay, but we figured out NO was second order. Okay, now what trials would we compare to figure out the Br2, the bromine? We would look at trials 1 and we would look at trial 3. Because between trials 1 and trial 3, we held NO constant, 0.02, 0.02, and we changed the bromine. So what did we do? We did, 0.04 divided by 0.02, that's 2. And then if we do 19 divided by 9.6, basically, right? So 19 divided by 9.6, 1.97, 2. All right, so we doubled bromine and the rate doubled. That means bromine is first order. So we know that Br2 is first order. Okay. Specification. Looking at trials 1 and 3, we doubled the concentration of Br2 while keeping the concentration of NO constant. And the rate also doubled. Okay, so boom, we got our orders. Okay, so then the next step, it says write the rate law for this reaction. So all we would do is say rate equals K times the concentration of NO squared times the concentration of Br2, and that would be it. And I'll touch this up a little bit. Okay. All right, now it says calculate the value of K and include the units. So first, let's just look at the units. Okay, so we know the reaction order is 3, right? So let's just get the units and then we'll actually calculate the value. We know the reaction order is 3. Where did that come from? 2 plus 1, the sum of the reactant orders. Okay, and so what does that mean? It's going to be 1. So the units for K are going to be 1 over molarity squared. Let me make it better here. Let's just do an equation. We're going to say 1 over molarity squared, and it'll be insert times, and remember it was seconds. Whoops, that didn't work out the way I wanted to. Times seconds. Now, why did I say seconds this time instead of just time? Because if we go back, remember they gave us the unit of time that they were using in this experiment, and it was seconds. So that's why it's seconds. Okay. Now let me see if I can touch this up without really. Okay, hold on. Let me give it a time. So while we're waiting for the Word, are there any other questions? This is a good time for questions while we're waiting for Word to come back and respond. Whenever I use this part of my Word document, it doesn't respond for a couple seconds. So while we're waiting, let's see if we have any other questions. And I'll check my email too. Did we get it? All right, we got it. All right, so that's what I wanted. So 1 over molarity squared times seconds. Okay, that's my units. Now, the other way to write them would be liters squared times moles to the -2 times seconds to the -1. Right? So this would be the other way to write the units. Okay. All right, but we actually have to calculate it. So again, we're going to have to plug in data. So you can pick any trial, but don't mix and match trials. Okay, so we just have to plug in data. So the rate was 9.6 times 10 to the -2. So zero 0.096 equals K, and the concentration of NO was what? 0.02. Okay, we've got to square that times the concentration of bromine, which was also 0.02. I'll go back and double check that. But we're just plugging in the data. I'm just trying plugging in the data from trial one, right? Yeah. So I'm just plugging in these numbers from trial one, and so we have all the numbers except for K, right? So I just got to square that. Okay. So we'll solve for K. Oops. We'll solve for K, and it's not capital K. It's lowercase k for rate law constant. So it's going to be 0.02 squared times 0.02. Okay, 0.096 divided by that. So it comes out to be 12,000, and these would be my units. Okay, so that would be our answer for part C there. Okay. Okay. So we'll keep going here. All right. Okay, so it says, what is the rate of disappearance for NO in trial two? Okay. So if you know the rate of one thing in your equation, whether it be the rate of disappearance of a reactant or the rate of appearance of a product, all you have to do is use stoichiometry to figure out the rate of anything else. Okay? So notice that this is a 1-to-1 ratio. Two of these for every two of these. So what we're saying is for every two of these that appear, two of these are lost. So the rate of appearance of NOBR is going to be the same as the rate of disappearance of NO2, of NO. So trial two, this is the rate of disappearance of NOBR. So what's the rate of appearance for NO? It's the same. So what was that, 3.8? So it'll be um, 0.038 molarity per second. Make sure you include units. That's the rate of disappearance. So you're gaining this much of the NOBR, but you're losing for every amount of NOBR that you're gaining, you're losing the same amount of NO. How do I know that? It has, a 1-to-1 ratio, 2-to-2. Okay. Now, let's do that same question, but what if it asked for the rate of disappearance of bromine instead? What you would do, if it was asking for the rate of disappearance for bromine, like that, okay, you would take your rate of disappearance the rate of appearance of the product that you were given, and you would multiply by the mole ratio. And you would say 1 mole of bromine for every 2 moles of no. Oh, sorry, moles NOBR. All you would have to do is multiply by the mole ratio. But you only lose 1 bromine for um, every 2 moles of NOBR formed. 1 mole of bromine is lost. All right, so you're going to lose bromine uh, at half the rate you're losing NO, or you're going to lose bromine at half the rate you're gaining the NOBR. So it would just be 0.038 divided by 2, and it would end up being 0.019 molarity per second. So this right here would be the rate of disappearance of the bromine. This right here is the rate of disappearance for NO in trial 2. Okay. All right. So here we're given 2 mechanisms. So this is mechanism 1, this is mechanism 2, and we have to choose which one's the right one. So remember, what did we discover? We discovered that the rate law was rate equals K times the concentration of NO squared times the concentration of BR. Okay, so we know BR2 is first order and NO is second order. That's what we know. So how do we figure out which one is right? So let's say this is the mechanism. Let's see if it works. Okay, so first off, double check and make sure it adds up to the overall reaction. All right, so N2O2 is an intermediate, and you end up with 2 of these plus 1 of those, you'll 2 of these. That's the overall reaction. If this is the slow step, bromine shows up once, NO shows up twice, NO is second order, bromine is first order. That's why this is probably the right answer. But let's go check this one. Okay. Okay. In this case, the BR is an intermediate. Okay. And you end up with 2 of these plus 1 of those, you'll 2 of those. And that ends up with the same reaction. So both of these mechanisms add up to the right equation, the correct equation. But if this is the slow step, then the rate law should show that bromine is first order and NO is zero ordered, right? Because NO doesn't show up until after the rate determining step. Okay? So if the rate equation, if the data had told us that rate equals K times the concentration of bromine, if we knew that if this were the rate law, if this right here were the rate law, if that right here were the rate law, this right here would match up with that mechanism. But that's not the correct mechanism, right? So this is the right one. All right, this is the correct answer. Okay, whoops. Let me. And the justification is this. I'll keep it up. This mechanism shows that NO is second ordered and BR square or BR2 is first order, which agrees with the data. All right, there you go. All right, and that would be it. That's the quiz. Okay. All right. All right. So that's the lesson for this week. I'm thinking about getting on Thursday again and doing another lesson for integrated rate laws. That'll be the lesson for next week, but we kind of have to move fast. So let me open it up for any questions. If you have any questions, there's not many people here watching, so I'm guessing people are going to plan to watch it on their own, which is fine. Again, we're getting a lot of mixed messages from the county, um, and our administration and stuff to be so synchronized means we do meet at normal class period times. Asynchronous means we just post stuff for you guys to use on at your own time. Okay. So we've been kind of told to, do it how we think we're going to, what's best for us, but also they kind of want us to shy away from the Blackboard Collaborate because it might not be working well. Okay. So tomorrow I plan to hold office hours at normal time. Remember, you got two choices on Wednesdays. You got 12 to 1:30 and you got 3 to 4. All right. I plan on having those in the Blackboard Collaborate sessions. So through Blackboard, you go to the Blackboard Collaborate Ultra, you go to those sessions. I plan on being there. If you can't make it, like if you can't get in for some reason, then email me at fcps.edu and let me know. And what we'll do is if I get enough people saying they can't make it into the session, it's not working, then I'll go to YouTube for the office hours like we did last week. Okay. What I'd like to do is kind of, dip our toe in the water and Blackboard Collaborate tomorrow. And then maybe that's what we'll use going forward if not as many people are using it because we've been told by the county not to rely on that. Okay. But we still can try. Okay. The reason why I wanted to come on YouTube is I think I have an easier time navigating and I feel like it shows the screen a little bit better than the Collaborate Ultra for the lessons. But we don't need to be live. You know what I mean? So we don't need to be live. I could just use YouTube and make the video. But what I want to do is kind of announce when I'm going live so the people that are available can come and ask, questions if they are available. And then those of you that aren't available during the live time, you can watch it on your own. All right. For those who have already done the problem set the past couple of weeks, are their new assignments have well, okay, so I just posted practice test number 3. I'm going to go over that on Thursday. You can work on that. I just assigned, remember, there's all that practice you can do in AP Classroom that I've assigned to you. So feel free to go do that. I just assigned a new one that's practice on reaction mechanisms. I kind of went over it, you know. So that's where I would go. Okay. But for unit practice, go to chapter 14 in your book. Look at all of those practice problems. Go to the unit. So all the unit 5 material that I've assigned you through the AP Classroom for AP College, the unit 5 stuff, their unit 5 is our unit 7. Do that as practice. Okay. That would be good. Yeah, I think so too. I think it shows the screen better. I don't know. I guess if I was just doing a straight PowerPoint, then maybe, but I feel like I like to be able to type stuff and kind of go on the fly a little bit. So yeah, so do the practice tests, Amelie. Do the I'll be Thursday afternoon. I'll go over the practice test and post the key, and then we'll do the same thing again next Thursday with practice test 4, and then we'll do the same thing the week after that with practice test 5, and I'll probably be making a couple more practice tests as we're getting closer and closer to the AP exam. And what I'll probably do too is I think I'm going to do a recorded lesson on Thursday morning for integrated rate laws. We'll see. I might wait until next week to do that. But I think I'm also going to post later this week the Unit 7 test, which will be kind of a take-home test. And it'll just be more practice for you on this particular unit. But if you want more practice right now and you've already done all the stuff that I've assigned for the Unit 7 stuff, then go to the AP Classroom, the College Board Classroom, and look at that stuff. And again, it would be labeled Unit 5 for them. Okay, and I also made another assignment for just reaction mechanisms. That's on the AP College Board Classroom. Okay. Yeah, I agree. I agree with the chat delay thing, and that's why we're gonna try collaborate tomorrow for office hours. So even if you don't have anything to come, like I strongly suggest like log in and just say hi or something, and let's just see if it works. It would be a nice thing to do. So from 12 to 1:30 or 3 to 4. I already have some people who have already asked me for retakes tomorrow, and we can do those. But again, if you can't get in to the Blackboard site for some reason, and I'm just sitting there waiting for people to join me, email me, let me know, and then we'll go to YouTube if we have to. Okay. Yeah, I agree. The chat delay is annoying, but yeah. Okay. So another thing is, guys, check your emails just real quick. Like College Board sent me a link that I guess they surveyed all the students like a week ago or so, asking, "Do you still plan on taking the exam?" And then they gave us the results of our students, and I had maybe six students say they were taking the exam, and the rest of the students were unknown because they didn't take the survey. So what does that mean? It means students aren't checking their email. Uh, you know what I mean? Or students are ignoring stuff from College Board. Don't ignore stuff from College Board. And I'm speaking to the choir. I know the people who are currently in the chat are probably the same people who've answered the survey and understand what's going on. This is more for people watching this video later, going, oh man, I better check my email. College Board might have sent me something. They're still planning on sending you a test if you haven't responded to the survey. But it was kind of shocking that only like six of you actually responded to them. So it's either A, you're not checking your email, or B, you're ignoring stuff from them. And if you're ignoring stuff from them, like, are you still planning to take the test? That's kind of the main thing. Um, you know. All right. So anyway, if you don't have any questions, I'm going to shut this one down. And I'll post the link to the video for the people that need to watch it. Okay. So I'll wait a couple seconds, see if there's any more questions. Okay, so for those of you that are ahead of the game, try practice test number 3, and I'll meet you Thursday afternoon to go over it. But again, if you can't make it live on Thursday afternoon to go over it, I'll post a link to the video so you can check that out. And I'll also post the key as well. But we'll do that on Thursday afternoon if you're ahead of the game. All right? All right. Later. Thanks for coming.